Good evening to everyone. First of all, I would like to wish you a Happy New Year, of course. And also, second, to thanks once more to Tavi for organizing and keeping alive this seminar series of the IGS. I'm not going to give a speech to you as IGS president or anything like this. I already sent you my Christmas message, so everything is told there. Just to remind you that it's important that if you have not done so, you should pay your 2021 membership. And well, I should recognize that I feel somehow nervous, and mostly because I hope that you do not expect too much from me, because I'm a simple glaciologist who knows a little of everything and probably not much of anything. So, as I said, you should not expect too much from me. But I'm just simply going to present some work done in recent years in the South Shetland Island area of the Antarctic Peninsula, which is the area where the Spanish Antarctic stations are located. It's mostly work on mass balance. But before that, I would like to spend just 1 minute to render a tribute to some relevant IGS members whom we lost during 2020. So I have some small slides. I'm not going to talk about them because this will appear on the ICE bulletin, but I think it's just good that we just remember to these people, starting by Gunnar Ostrom, who was really a king of the mass balance. I will be talking today of mass balance, and really Gunnar did a really extraordinary work on the observational aspect of mass balance, and also was a pioneer on remote sensing of glaciers. Second was Anker Weidig. I just selected 6 of them. And this was a person who did a lot of work in Greenland and was working in really many different aspects of glaciology. Also, as you know, we lost to Connie Steffen, and in this case was a tragic accident through a crevasse. And all of you know his work, mostly in Greenland, automatic weather stations, mass balance, and so on. Also, we lost during 2020 to our former Secretary General, Simon O'Mani, and this was also an important loss for the IGS. Also, Wendell Tangborn, who did also a lot of work, in particular in glacier hydrology and also in mass balance. And finally, another famous glaciologist who left us in 2020 was Will Harrison, who did really lots of work, especially on glacier searches, also on fast flow of glaciers, and did really a lot of instrumental work also in using various geophysical techniques. So this was just small words, just to render tribute to these people whom we lost during 2020. Of course, probably I'm sure that we lost some more, but these are just known people or people whom I had the opportunity to meet at some time. Okay, so after this, I'm just switching to the presentation, to my own one. Let's see. I'm just trying to, just a second, sorry, to, what is on the other side? It's because I have a problem because the menu bar does not disappear from the top. Usually it disappears automatically, but it's not doing, and then it's covering part of my slides. So it's, well, okay, let's start. The title of my presentation is Hiatus of Mass Losses from Hurd and Johnsons Glacier, Livingston Island, during the recent regional cooling period experienced in the Northern Antarctic Peninsula. Here, this is myself, what you can see. By the way, I'm going to switch on the laser pointer, which will be better. So, in fact, here in this photo, I'm just standing on one of these glaciers, Hurd Glacier, under really nice weather conditions, just doing some GPS measurements around. Okay, this is just the sketch of the presentation and the outline, and I'm not going to go through it. I will start just through the study site, especially for the glaciological and climatic setting. And within the climatic setting, I will be talking about this recent cooling period in the Antarctic Peninsula region. And then we will analyze the impacts on the cryosphere, starting by surface mass balance, then total mass balance. We will compare not only these particular glaciers, but also other regional glaciers, and also the geodetic mass balance for the South Shetland Islands, and also other cryospheric and environmental impacts of this recent cooling. So let's start with the glaciological and climatic setting. The couple of glaciers that we are going to analyze with more detail at the beginning of the presentation, in particular, are Johnsons and Hurd glaciers. These glaciers that you can see here in the map are located in the Antarctic Peninsula, which is this small peninsula that you can see here, within Livingston Island, that is part of the South Shetland Island, which is this archipelago, which runs more or less parallel to the northern part of the Antarctic Peninsula, which is known as Trinity Peninsula. So we have this couple of glaciers. This is the ice divide. There are two main basins. What is here in white are also glaciers, and these indicate approximately, there are three different basins, sea terminating, but these are heavily crevasse ice falls, so there are no really studies there. So most of our studies are done in these two glaciers. This glacier has the particular circumstance that is tide water, so the flow is in this direction. And this other one is the more convex ice cap, which has a few lobes or tongues, which are saline rocks, Las Palmas and Argentina. You can get an idea of these glaciers through this photo, where you can see here the Hurd Glacier, which is more like an ice cap, which is connected to Johnsons through the ice divide. And Johnsons is tidewater, as you can see here. You can see the calving front here. And also these two glaciers, the main reason why we are studying these two particular glaciers is because they are located really close to the Antarctic Spanish station, Juan Carlos I. And we have behind here the Mount Friesland with 1,700 meters. And well, you see here that the location, approximate location of these islands, which you see, which is not that farther south, it's just 62 degrees south. This is a polythermal ice cap with a small altitude range, just from sea level to around 330 meters. And Johnsons and Hurd Glacier, these two different units that we will be studying, have surface areas around 5 and 4 square kilometers. Average thickness is quite similar, around 100 meters for one, 90 meters for the other. And the maximum thickness is largest in Hurd Glacier with 200 meters, while in Johnson's Glacier, even if the average thickness is slightly larger, the maximum thickness is smaller. Important thing, as I mentioned, is that Johnson's Glacier is a concave basin, so the shape is quite different, and this will have an influence on the accumulation regime because of the prevailing winds, as I will mention later. While Hurd Glacier is a convex lobed ice cap and is land terminating. All of this, Argentina, Las Palmas, and so on. Around 60 years ago, Las Palmas was ending at sea, but at present, I mean, since probably around 40 years ago, it's just all of them are land terminating. This is just a more detailed picture of these glaciers. You can see probably the grain, but this is because these are digitized from all the slides, and hard in this case. Okay, so talking about the climatic setting, the important thing here is that we had an intense warming trend in the Antarctic Peninsula during the second half of the 20th century. And so there were a set of papers, mostly by Turner and other colleagues at the British Antarctic Survey, who analyzed the temperature trends in the Antarctic Peninsula region. They published this famous paper, well, a set of papers really, pointing out the strong warming trend observed at Faraday-Bernatsky station, which you can see here in yellow. Is above half a degree per decade. And even for the winter, this will be for the annual temperature, the trend, and for the winter temperature is above 1 degree, which is extremely high, of course. Something doesn't advance at this moment. Okay. So as a consequence, we have seen really many times a repeated message in the literature, in the sense that the Antarctic Peninsula is one of the regions showing a largest warming trend on Earth. But we will see that there are really marked differences across the Antarctic Peninsula region. So that means that this is not the same for all of the Antarctic Peninsula. And in addition, we will be talking about a recent temporary cooling trend. Starting with the analysis by Turner and colleagues, which was published in Nature in 2016. The first thing to stress is that they were analyzing what is called the stacked temperature record, in the sense that what they were studying was, they were piling up all temperatures from all different stations. So in particular, they were analyzing the data from the 6 stations that you can see here on the map, which have the longest temperature records in the region, which are starting. The oldest one is from Bernatsky, are starting around the 50s, then some are starting in the 60s, 70s, 80s, and so on. So there are a set of these stations that you can see that all of them are above the position of Rothera. So that means they are in the northern part of the Antarctic Peninsula. And as I mentioned, they were doing this stacked temperature record on the basis, I will just stress what is in red here, in the sense, why did they analyze the stacked temperature record? Their main reason was that the fact that the surface air temperatures for all 6 stations that they were analyzed had a similar relationship with the mean sea level pressure. And as a consequence, a similar relationship with the broad scale atmospheric circulation. So they've just analyzed the whole, let's say, as a trend for the whole of the Antarctic Peninsula. They were using some statistical techniques, analyzing these records, as we will see here, this Mann-Kendall test, for determining the turning point, the inflection point in the, well, the maximum, in fact, the turning point in the warming trend. And what they determined, well, you can see that the temperature record they studied was actually from 1978 to 2016. And this was basically, or 15, but this was basically because they wanted to limit to the period where they had also the satellite record, because they were doing comparisons with, for instance, to the sea ice concentrations and other various parameters, and then they decided just to limit the study to this period, even if the oldest temperature records go back to the 50s, as I mentioned before. And you can see here the trends. This record was characterized by a warming trend between 79 in 1997 of 0.3 degrees per decade, and a much stronger cooling trend starting around 98, 99, which was the turning point that they determined, quite close to minus 0.5 degrees per decade. So a warming trend followed by a even more intense cooling trend lasting for more than 15 years. Concerning the explanation of the changes, I can skip this one because it's detailed in the next two ones. So I will just go straight to them if I can move, because it sometimes gets stuck. Okay, like this. So in this first one, what we are seeing is the trend in the annual mean sea level pressure. And the important thing, so this is just to explain the changes that we have been observing on the temperature, the transition from the warming to the cooling period. During the first period, the warming period, the standard period that was, let's say, the continuation of the last 50 years in the Antarctic Peninsula region, you see that there are no big changes in the trends of the mean sea level pressure. And however, in the second period, you see here a strong negative anomaly, which means a reinforcement of the low pressures, of the belt of low pressures around Antarctica. As we are in the southern hemisphere, then we have around the low pressures, we have the clockwise prevailing air direction, and this means that there are winds coming from the east and southeast to the Antarctic Peninsula. It's quite lazy for moving the computer. I don't know why. As a consequence of this increase of the easterlies or southeasterlies with respect to the northern part of the Antarctic Peninsula, what has happened is an increase in the sea ice concentration, which is the one that has accompanied this decrease in the temperatures and has strengthened this increase in temperatures. So what we see here is the trend in the annual mean sea level concentration. Well, compared to the study by, before leaving Turner, I should mention also important comment is that they made, Turner and others, that these decadal temperature changes in the region are not basically associated with the main drivers of the global temperature change, but instead they are an expression of natural internal variability of the regional atmospheric circulation pattern. So this is some kind of saying that we should not say that, that this is internal variability, which has been stronger maybe than the global whole Earth variability in the sense of warming, and here has prevailed the cooling during this short period, but it's not something that is going to last forever, because in fact it has already come to an end. Where just 1 year after this paper, we published another one, Oliva and others, is a colleague, about the spatial variability of the temperature trends across the Antarctic Peninsula. And in this particular case, what we did is analyzing the whole historical record for each of the stations in the peninsula. Not only these 6 they analyzed, we use a total of 10. We were analyzing the regional variations, so the geographic differences within or across the Antarctic Peninsula. We were also analyzing the seasonal variations, how the changes were different in summer or winter and so on. As I said, we analyzed the 10 stations, and also in this paper we analyzed some observed impacts of these temperatures on the cryosphere. So first of all, we are showing here the distribution. Well, you can see here the whole set of stations. This here has a zooming here, because this is the South Shetland Islands, because we have 3 different stations there: Bellinghausen, Mars, and King Sejong. So we have also 3 stations in the northern or northeastern Antarctic Peninsula: O'Higgins, Esperanza, and Marambio. And we have also Orcadas. Orcadas is included, but anyway, somehow an outlier in the sense that it's far from the Antarctic, strong Antarctic influence. And then we have the set of 3 stations in the southwest which include Faraday, Rothera, and San Martin. And then this figure is important because what we are showing here are the decadal average temperatures. You see that they are negative, not really so much negative, but they are, you see the increasing trend. So with the time, these are decades, and then they are increasing temperature. They are every time less negative. But this is what happens in the stations in the southwest, because if we go either to the northeast or to the South Shetland Island, you will see that in the transition from between the two last decades, from red to gray, here you see that there is a cooling, a systematic cooling in all of them. You see absolutely all. Orcadas is weaker and totally different from this. So this is first expression of the differences that I was mentioning, that we were talking and we are used to talk about Faraday record, and not everything is like Faraday in practice. In fact, this cooling has been only observed basically in the South Shetland Islands and the northeastern Antarctic Peninsula. Okay. In this particular case, we are seeing the temperature evolution. Well, it's really of the anomaly with respect to some average of the monthly air temperatures. For all of the stations, there is a 3-year moving averaging in here. And then important things to see here. For instance, red and yellow, which are some of the older records, but the red in particular, red is precisely Faraday-Bernatsky. You see that these stations start from a much lower temperature and go to a high temperature, while all others have, of course, a smaller trend. And the slope is much smaller for this. Also, we see that important factor is that these gray bars are just marking the location of the very strong El Niño events, which we had 3 of them recently. One of them is really recent, so it's not in the record that we analyze in this paper or Turner. But important thing is that these El Niño events are also coincident with strong temperature increases in both cases, but then really, you see, really marked increases in temperature, but these are followed by some kind of more gradual decreasing trend. This here and much more marked in this particular case here, except for these stations, I will mention this, and that lasts about between 10 to 15 years or so. So strong warming, coincident with El Niño events, and then gradual and more slow cooling period. And this is the last, the cooling that we are referring for the last 15 years or so, is this one that you can see here. And you can see here, but you don't see these 3 stations here. Well, there are 4. These 4 stations here are precisely all the stations in the southwest Antarctic Peninsula, that instead of continue cooling, went up again. Are these 3 together with this outlier that we have, that is Orcadas station, that we should not pay that much attention. So this is important point, again, to distinguish what happens in Faraday as compared to what is happening in all others. So all others in this sense would be all the stations in the South Shetland Island and the northeastern Antarctic Peninsula. Finally, regard this, what is showing here is are the trends in the seasonal temperatures, and in particular, this is analyzing the change in temperature, an average temperature between the 2 most recent decades. And you see here the explanation for the squares, for these squares here, that we have here December, January, February. That means that we are in the southern hemisphere. So this would be the summertime, and June, July, August would be the winter time. Just marking this. Just to remark that again, the southwestern stations have a totally different behavior. You see that small decreases in the winter temperature, even some positive trend in this transition between the two most recent decades. Well, in the South Shetland, for winter, we have -1, -1.2, 3, and so on, and something quite similar in the Northeastern Antarctic Peninsula, as you see here. And also pay attention to the changes in the summer temperatures, which you can see here, are much smaller than the winter ones, just about ½ degree, both here and also in the northeastern, around 0.5 would be the average, the decrease in summer temperature. And this is the one that is going to influence the surface mass balance observed in these records. At the same time, in these stations, the things were much weaker, the changes. But anyway, the winter, you see the big difference, and the summer, even if this is small change, you will see that because of the high sensitivity of the glaciers in this region to small temperature changes that we will analyze some later, you will see that this small change has had important implications in the surface mass balance. So we are going to analyze the surface mass balance for the period 2002 to 16 for Hurd and Johnsons glaciers, so consistent with the dates that we have been analyzing also for the temperature record, more or less. And this will be the surface mass balance by the glaciological method. But before that, this is a summary. This is not really, it's a summary. I'm curious whether you see, can you see my bar, the menu bar for my menu bar for Zoom?
No, we don't see your menu bar. We just see your slide. Paco.
Okay. Okay, perfect. Because then it's because sometimes I'm removing the menu bar because it has become stuck on the top and then covers always the title. So sometimes I get somehow lost. Okay. Oops. Okay. Then these are just observed cryospheric impacts of recent cooling. It's just a small listing and we will go through all of them. We have been mentioning these changes in sea ice concentration, such as this increase in the northeastern part of the Antarctic Peninsula because of this increase in the easterlies in the Weddell Sea. We will talk some later about the increase in the snow cover duration and extent, and also in the decrease in the thickness of the active layer of permafrost. And also to mention here, this will be the only reference to this, that in the Northern Antarctic Peninsula and neighboring islands, Davis and others already noticed, before all of this thing about the cooling in the region was observed, they already noticed that between these two periods, which one of them is in the cooling and the other is in the early phases of the warming that we have been analyzing, the number of receding land terminating and takewater glaciers decrease by 11%, and the area losses decreases also by 8%. But most important, and we will be focusing mostly on the surface mass balance records, and in particular for those glaciers that have the records in the World Glacier Monitoring Service. And this includes these two glaciers that I mentioned, Hurd and Johnsons, but also some glaciers on the northeastern Antarctic Peninsula, like in Vega Island or James Ross Island. And what has been observed here, as we will see later, is that there has been a transition from predominantly negative surface mass balances in the previous decades to predominantly positive, meaning surface mass gains in the recent couple of, or 1.5 decades. And there are various references about this, but we will be talking about that. Okay, we have seen already which are our glaciers. Just to mention that these red spots that we see around here are the stakes for accumulation ablation measurements. We also do the snow pits and so on. And also is marked here the location of the automatic weather station that for which we will use some records some later. At present is located in this particular area. In fact, we have, that's curious. We set this station on the ablation area when we installed the station. But then suddenly that ablation area became an accumulation area, and then the station was useless there because it was so much covered by snow that was having, I mean, only in summertime when we were digging the station and putting on top of the hugest amount of snow falling. So it was still on ablation area, but this suddenly became accumulation area and persisted as accumulation area for quite a long time. They are around 50 stakes, and we also dig around 5 snow pits every year. And we are submitting the surface mass balance data to the World Glacier Monitoring Service since 2002 to present. Yeah, so these are just a couple of pictures here, just about that, just to point out that we are doing the snow pits for density measurements and also for snow stratigraphy. We are also doing of course, we have a large set of stakes for mass balance. We use both for mass balance measurements, accumulation and ablation, both, but also we are using for velocity. We are doing repeated measurements by differential GNSS, GPS, if you want, which means that we are also using this for keeping track of the average velocities at a set of about 50 points on the station. We have here Gunnar Ostrom, by the way, who was there. Okay, and so of course we have to re-drill the stakes in the ablation area because they become exposed, and we have also to, or they become buried in the accumulation area, and so we have to do the usual maintenance of the stakes, and then with the mass balance readings and the densities of the taken in the snow pits, we do the proper conversions to get the for each of these around 50 points, the winter balance, the summer balance, and also the annual balance, as we can see here. This is just an example. This is for the hydrological year 2005. That means the 2004 to 2005. So it's the year ending at the end of March of 2005. And of course, we do the integration of these values and multiply by the corresponding areas and so on to get the whole glacier, the mass balance for the whole glacier, both the winter, the summer, and the annual. And of course, we also determine the equilibrium line altitude and the accumulation area ratio by the usual procedures, many of them really well defined by Gunnar Ostrom, whom we mentioned before. So here is important thing that is what we can see here. These are the our surface mass balance series, in this particular case for Johnson's Glacier, for all the hydrological years between 2002 and 2016. And then, well, we need to explain the, well, probably most of you are used to this. We have for each year, we have the upper part of the column represents the winter accumulation, the white column, and then the gray part is representing the summer melting, the summer balance. And then to the right of the column, there is another, which is red if it's the annual balance is negative, or it is blue if it is positive. And what can we see quite quickly in this image is that we were switching from until 2009, in particular, until the hydrological year 2009. In the particular case of Johnson's Glacier, balances were more or less around zero. But starting in that year, they have been consistently, all of them positive, as you see. And there is some kind of, you could imagine some kind of increasing trend that we will show some later. In the case of Hurd Glacier is characterized by always by more negative mass balances as compared to Johnson's. I will mention why some later. And you see here that there is a clear transition. Again, is the year 2009 is the last one of the negative series. And then this is mostly dominated by positive mass balances, except this small exception here. Okay. So this is something that is not seen really in that many places on Earth at present, to have systematically during years positive surface mass balances. And we could wonder, of course, what is the main reason of these changes? Is because of there is less melting? Is because there is more accumulation? Or both? And really, the reality is that both things. It depends on the year. For instance, there are years where the positive that we see here is mostly due. I didn't mention that these dashed lines on top and below. This is the average for the 14 years, the average winter balance, and this is the average summer balance for the year. That means this particular year, for instance, the summer melt was like average. However, there was a large accumulation, which was the one causing this positive mass balance, annual mass balance. But in this particular case, let's say, it's opposite. Let's say that the accumulation is around quite close to the average, but there was a really small summer melting. Or we have a case where both things are happening together. We have a huge, a larger than usual accumulation. Well, you can notice the typical values here. So this is, in these glaciers, there is not that much accumulation. It's just the average for these 14 years is 0.8 meters water equivalent. And regarding the melt has been 0.7 or something like this. In this particular one is Johnson's. And so, as I mentioned, we have a really huge accumulation and really small melting, and then we get a really record positive mass balance for that particular year. Here we can see just the summary of the, we see here the summary of the averages and also the variability. So what we have here is the average and the standard deviation of just this slightly smaller, the number is the standard deviation of the 14 annual measurements whose averages are shown in the first line. And then things that we can see that we have a nearly zero surface mass balance for Hurd and positive for Johnson's. So the annual, the average is slightly negative, but it's nearly nothing, because this compared to the error of the measurements, that would be at least 0.1 meters water equivalent. This means this is a zero. And the slightly positive for Johnson's in the period. Also, that's important that the larger winter balance for Johnson's compared with Hurd. And this is basically, so the winter balance. Winter balance, you can compare, the Johnson's is much higher than Hurd. But they are next to each other. And what is the reason for this? The reason is what I mentioned. Johnson's is a concave basin, tidewater basin, which is north of Hurd, which has a convex shape like any ice cap. And the prevailing winds in this area are from the south, south at least. And this means that most of the accumulation of the snow that falls on Hurd Glacier, especially in the highest parts, gets diverted, gets deposited on Johnson's Glacier, where so it's redistributed by wind from Hurd to Johnson's. So there is a strong and constant snow redistribution from Hurd to Johnson's, which is causing that the accumulation is always higher in Johnson's compared to Hurd. Then, of course, you can see also here well, we will analyze later the evolution of the ELA and the accumulation area ratio, and which are rather small. And you see this asterisk here. The asterisk is mentioned here. That means that we had in the recent years 3 years for Hurd and 2 for Johnson's, where we had 100% accumulation area ratio. So that means all of the glacier was like accumulation area, and the ELA correspondingly, of course, was at sea level. So that is important. So also concerning the maybe perhaps fitting the last one, that for both glaciers, there is a higher variability of the summer balance than the winter balance, and this is more marked for Hurd. I will make a reference to this in some later slide. Here we have some correlations, and in these correlations, I think I'm going to stress. I'm trying. Okay, I will just comment on two of them. That first, what we have up here are the correlations between the corresponding values for winter balance, summer balance, annual balance, ELA, and accumulation area ratio between Johnsons and Hurd. And you see that the value that is most correlated is the summer balance. And second, I will point out this, and is that the positive correlation between the summer and the annual balance is much larger than the positive correlation between the winter and the annual balance. And this means, in other words, that the annual summer mass balance variability is dominated by the summer mass balance variability. So this is the one driving the, let's say, the temporal changes. So we have now a set of slides about the evolution of these trends. We start with the surface mass balance evolution for Hurd and Johnsons with some linear trends that you can observe here. To the right, and there is also here always in each case the Pearson correlation coefficient between both time series, and you see that there is this. This is meters per meters of water equivalent for the annual balance, and you can see here the slopes, which are quite significant. In fact, for this period, they are starting from these values to these values in just 14 years. It's also interesting to see what happens with the cumulative surface mass balance, which has been the surface mass balance of adding 1 year after the other. And you see that for Hurd Glacier, basically, as I mentioned, it was quite close to equilibrium as regards to surface mass balance. Notice one thing, that is Hurd Glacier is land terminating. That means that the surface mass balance is the same, is approximately equal to the total mass balance. So this one is like in equilibrium. And in the particular case of the other one is the darker blue is for Johnson's Glacier, which is the tidewater one. And in this particular case, you see that has increased from the starting in 0 up to 1.2 meters of water equivalent of increase along these 14 years, which is really also quite a notable value as compared to the rest of records in the world, of course, because this is such positive values. Of course, the point is that when we add to this one the calving, then it goes down and gets really quite close to the other. So they are nearly both for this period. On average, they have been in a steady state regarding mass balance. Well, next we see we have here the equilibrium line altitude evolution during this period. And again, you see that we were starting from values around the 300 or 200 meters, depending on the glacier. And in the case of Johnson's, which is the tidewater one, is lower equilibrium line altitude. But starting from these values to the current values, which are between 50 and 100, and sometimes, as you see, as I mentioned, go to 0, the equilibrium line altitude. So a really descending trend, quite marked. And opposite for the accumulation area ratio, where you see that we were starting from values of accumulation area ratio rather low in the case in particular for Hurd Glacier. Johnson's were about double, and we are ending in values around 90 with the time series. I mean, with a straight line fit. But anyway, even with the real values, you see the thing here. So these are kind of records which are not really seen in many glacier regions in the world. I know that, for instance, there was some years also in New Zealand where they have this kind of things, quite recently, in fact, but it's not that normal. We are now going to compare the surface mass balance. We are going to add the frontal ablation in the case of Johnson's just to get the total mass balance, and we will compare also with the geodetic mass balance analyzed by separate. So we will have the surface mass balance plus frontal ablation, but we have also estimates of geodetic mass balance for these glaciers for 2 different periods. Okay, then just to remind that for the total mass balance of Johnson's and of Hurd and Johnson's glacier, let's remind that as Hurd is land terminating, the total mass balance is approximately equal to the surface mass balance, assuming that negligible the internal and basal mass balances. Well, I'm saying surface mass balance, we could say climatic mass balance if you want, but then in that case, it would include the internal balance, internal accumulation at least. But then they are equivalent, so there is no need to just to distinguish. In the case of Johnson's, it is tidewater, and that means that the total mass balance would be the sum of the surface mass balance plus the frontal ablation. But in the particular case of Johnson's glacier, we have the situation that we have a stationary front position for many, many decades, has been nearly not moving. You should know that the bed is totally, the bay, the proglacial bay that is in front has a really low depth. Sometimes it's just a couple of meters just in front of the glacier, on the glacier front. You have maybe 30 meters of the cliff, but then below the water there are just a couple of meters, and then it is rather flat, and then it has been stagnant there, moving up and forward. I mean, a few meters up out glacier, a few meters up glacier, but really has been nearly stationary. And this has and also for our computation, we have been setting the flux gate at the Kelvin front, and we have also negligible submarine melting, and all of this implies that the Kelvin flux is nearly equivalent to ice discharge and also nearly equivalent to frontal ablation. Okay, so we can get the total mass balance just adding this estimate of the Kelvin flux by discharge through a given flux gate, which is located on the glacier front. In fact, here is how we did this calculation. We don't have a stake measurement right at the front, but we were combining 3D full Stokes dynamics model tuned with the stake velocities, with all of them, but with a special weight for those which are close to the Kelvin front. And from this, we obtained the set of velocities as a function of depth at the different points in the Kelvin front. And then we computed this column average velocity. And of course, this integral was computed in a discrete way, just making some kind of bins of area where we had the average velocities for each of these bins and the area value, and then we just did the sum. And what we got is this kind of values, which are really, for people used to other glaciers, will think that they are ridiculous. We have here just this small amount of volumetric Kelvin flux in these particular cases in cubic meters per year times, so it's something like 10, it's like 1 million cubic meters per year. And if we divide this by this amount by the total area, surface area of the glacier, this would be equivalent to a surface mass balance of a negative, of course, because there are lost Kelvin losses, of minus 0.14 meters in water equivalent. We also did an average, we also did geodetic mass balance estimates for 2 different periods, in 1957 and 2000 and 2013. This was done by the usual procedure of them differencing, and the DEMs were obtained. In the case of 1957, was from by photogrammetry from British aerial photos from the, people sometimes say the British Antarctic Survey. At that time it didn't exist. So it was really the Directorate of Overseas Surveys of the UK. And then from that, we got these DEMs. And in the case of 2000 was from geodetic measurements using theodolite class laser ranger for Johnsons, and using differential GNSS in the case of Hurd. And in the case of 2013, it was totally using differential GNSS. And you can see in the next slide the results of this for the periods 57-2000 to the left, and then 2000-2013 to the right. And here you have the total geodetic mass balances computed in this way, but here you can see also the spatial distribution. And you see that there is, you can appreciate that there is, let's say that here you see that the yellow is the zero, is around the yellow, and then these are increases and these are decreases. And notice that these are surface elevation changes. But well, of course, they are related to the geodetic values, just using the proper density. Proper density that was not a standard value, but was used different densities in the areas that were covered by ice and those that were covered by fern. And so we see just yellows are the zeros, that you see that there are more zeros here, but there is still important thing that there are in Johnsons, there is, let's say that it's becoming more and more concave because it's like falling down, while the upper part of Hurd is nearly stable, but there are certain areas where you can see the blues, which would be the increases. But really, if you analyze the geodetic mass balance for these periods, you see that there is, for Hurd, and first period, second period, that so there is a decrease in the geodetic mass balance between the last 50 years of the last century and these 13 years of this new century. There are some decreases, but they are not that big as you would expect. But I should note also that this is partly because this is starting into, we have been seeing 2002 to 2016. 2000 and 2001, even if we have not mass balance measurement, were really warm years and with a strongly negative mass balances, because at that time there were some mistakes in just in Johnson's glacier, and then were years with quite negative values, and the most positive are also excluded from this set. So if we had used here 2002, 2006, these values would have been much smaller and more consistent with what we have seen talking of the glaciological balance. Here is the total mass balance for two different periods. One period, just because we are, is 2002, 2013, because we want to compare with the geodetic, and so we want to compare the geodetic, which is total mass balance, with the mass balance obtained by adding calving and surface mass balance for Johnsons, or just surface mass balance for Hurd. And for 2002 to 2016, because it's the longest set that we have. And then what you see here is the surface mass balance values that we are different from those that we saw before, because these are restricted to 2013. This is the frontal ablation. The frontal ablation I didn't mention, but we had only the measurement estimate. Its base is only done as average for this period, 2005, 2008. So the velocities in these glaciers have not changed much, neither the thickness, which means that the values have been quite consistent, quite not changing. Well, then the total mass balance we get by adding the surface mass balance and frontal ablation are these values here, and these are the values obtained by the geodetic mass balance, which you see that are much closer to each other in the case of Hurd as compared to Johnson's. And this is probably related, I guess, to some kind of problem with the estimate of the frontal ablation or the variations in the frontal ablation between the various periods. And what we have here is the total mass balance for the whole period, for which we have here the values that we saw before, but now together with the frontal ablation, we get the total mass balance. And as I mentioned earlier, that you see, we had seen this and we had not seen this. So Hurd was close to balance, around 0, slightly negative. Johnson's is close to 0, slightly positive, but nothing, because it's, I mean, nothing compared with the probably the error. So conclusion, both glaciers have been nearly in equilibrium during the period 2002-2016, and this is consistent with other evidences for geodetic mass balances, for instance, by this study in preparation by one of my PhD students, Kayan Fernandez, and which I will show later some values for these geodetic mass balances for the whole set of islands within the South Shetland Islands. Sorry, I had this. So we are now going to compare with other surface mass balances in other glaciers in the region. And these glaciers, just to, I will show the graph, but just to situate yourself, we have in Livingston, we have Hurd and Johnsons. In King George, we'll have the Bellinghausen Dome. And in Vega Island, Northeastern Antarctic Peninsula, we have Bahía del Diablo Glacier. And finally, in James Ross Island, we have Whiskey and Davis Dome. This is run by Argentinians. This is run by the Czech people. And then we have here the records. This is not that easy to distinguish or to see, especially for colorblind. I'm sorry. I should say that I'm also partly colorblind, so I have some difficulties also. But important thing here, so for instance, it's just important to notice this green is Johnson's. As you can see here, that Johnson's has always the most positive, or if they are negative, the least negative of all surface mass balances of all glaciers in the region. And also that Hurd is has the second most positive surface mass balances in general, but has also several very negative values. So in general, all of the, let's say that all of them follow a similar trend, but the most positive values are found in Livingston Island, basically. But we will see later that even for the geodetic mass balance, Deception Island is the other island where there is an Spanish Antarctic station, and it's also the one with the highest positive surface mass balance. That means that the stations, Spanish Antarctic stations, are located always on places with positive surface mass balances. Well, I will pass quickly through this one anyway, but it's just this is some surface. This is modeling of surface melt and runoff done by Kosti and others in 2018. And well, it's of interest because they did a study across the entire Antarctic Peninsula, but I wanted just to mention or to show how parallel are the records for the surface melts are the circles and the runoff are the squares. And this is for the South Shetland Islands and for the Northeastern Antarctic Peninsula, which is the location of all the other stations where there are surface mass balance records. And you can see that they, if you put one on top of the other, they are similar, but the values, of course, are much larger in the South Shetland Island. But it's also a special thing that I would like to stress in this figure, sorry, and it's this couple of comments here, that in the South Shetland Island, there is a marked difference between the melt and the runoff. And while here you can see that they are nearly coincident or quite close to each other. And what does it mean? This has important implications because in the South Shetland Island, this means that part of the melt gets refrozen and then is not lost. And so we can expect that the surface mass balance will be more positive. While in the northeastern stations, where we have seen in the previous figure that the surface mass balance values were less positive or more negative in the negative years, this is partly due because in this case, runoff and melt and runoff are quite similar in magnitude, which means that most of the melt is lost by runoff. So this is important thing to consider when doing this kind of studies. This is just to stress that in particular, this Costi and others did use our surface mass balance data for validation. They didn't use for calibration, they used but for validation. And the validation was quite good, and is what you can see here. On top we have the accumulation, and down here we have the melt. And the accumulation, in the case of the model, is from ERA interim reanalysis data, and the other are our observations in Johnson and Hurd. And here, in this particular case, is using for the melt a positive day approach for modeling the melt, and then the observational part is our own data. And you see that they quite fit really quite well, except for this particular year, 2003. So let's go now to the phase of explaining the changes, why these things are happening. Then, as we mentioned when we saw the mass balance series, the surface mass balance series, we saw that sometimes the positive were due to increased accumulation, sometimes it was due to a decreased melt, or sometimes to a combination of both. And then it is true that the decrease in the rate of mass loss between these two periods is partly related to the increase in accumulation rates that has been observed in the western coast of the Antarctic Peninsula, and associated to the deepening of the circumpolar pressure trough. And there are some evidences of this. There are more recent ones, but sorry that I forgot. I wanted to update this one, but I failed to do this. But there are certain evidences, such as increasing trend in winter accumulation in the northwestern Antarctic Peninsula from ERA 40 reanalysis. There is also annual total of precipitation days at Faraday-Bernatsky has been also increasing. This was studied by Turner and others. And also ice cores from the southern part of the Antarctic Peninsula, and also near the northern tip of the Antarctic Peninsula, have been showing accumulation increases over the second half of the 20th century. But mostly, let's see. But as they decrease, the decrease in mass losses is mostly due to reduced summer melt, and this is mostly because of lower summer temperatures, as we discussed before. What we have seen, what we have here is just the record of summer temperatures. This is in Bellinghausen. I took Bellinghausen because in Bellinghausen they have a longer record than in Juan Carlos I, but they have a really absolutely strong correlation. I have some other figures about the correlation between both the stations, Juan Carlos and Bellinghausen, which means Livingston and King George Islands. And you see that there is a strong anti-correlation, so they are like a specular image of each other. What we have here is the summer balance for Hurd and for Johnsons, as just following opposite the trends in the summer temperature, and with this rather high Pearson's correlation coefficients. Anyway, if you remember, the change in temperature that we had between the two most recent decades in summer temperature was just of 0.5 degrees of decrease in summer temperature. And we could think that this is not such a huge change as to justify this change from the negative to the positive surface mass balances. And then, however, what happens is that these glaciers have a really strong sensitivity to temperature changes. So even if the decrease in summer temperatures has been limited to this 0.5 degrees centigrade that I mentioned, minus, so they have decreased, modeling of melting in Johnson's and Hurd glacier has shown a strong sensitivity of these glaciers to air temperature changes. And in particular, this paper that is mentioned up there, Jonsel and others, the others are the Spanish team. This was a postdoc from Sweden that was working with us around those years. And that this study of the sensitivity to the melt modeling, it was using a combined positive degree plus radiation model for melting, and important result was just a 0.5 temperature change. In case of increase, implied a 50% increase in melt rate, and in the case of the decrease, by a 44% decrease for just 0.5. And moreover, the reason of this high sensitivity is that the summer average temperature of these glaciers is rather close, and then the glacial surface is really close to 0 degrees. That means that if you have just a few tenths of degrees of increase or of decrease, then can be a switch in the regime from non-melting conditions to melting conditions, or vice versa. That means, in the same way as the things have changed to this small cooling has led to an important shift to positive surface mass balances, a small change, a new increase in temperatures will correspondingly also imply a return fast to the strong melting conditions. So, what about the geodetic mass balance for the rest of the South Shetland Islands? I should be finishing this quite fast. Okay, then we have here, this is the work by my PhD student, Kayan Fernandez, which is work in preparation to be submitted in hopefully in a couple of months, let's hope. And what you see here is the different islands. We analyze all of the South Shetland Islands except Clarence and Elephant, which are farther northeast. You cannot see them, or Smith Island. And these were missed sometimes because of some lack of some of the data, because we were using DMs from SAR, from Tandem X, but also mostly due to the really huge slopes of the islands such as Smith, for instance, but it's also the case of Clarence and Elephant, which has huge slopes, and then means that it's not possible to get good quality DMs from the SAR data. And then I will just illustrate. It should be shown here. In theory, I should have, well, I think it's lost. I had a value somewhere here about the total value. Well, okay, let's go by islands just to see that the period analyzed for this is 2014 to 2017 for the different islands. And then in King George, this is what I don't want to give values in megatons per year, because this depends on the size of the island. So these are just the equivalent surface mass balance that will be equivalent to that. And you see that it's rather close to 0 for King George Island, which is the largest of the South Shetland Island. Then in the cases of Nelson, Robert, and Greenwich, Nelson is, you can see also through the colors, you have the color scheme here, that this is more, let's say, slightly more reddish, and that means that we have a more negative mass balance as compared, for instance, to this or to this, which are nearly 0 values. Then in the case of Livingston, we should point out that Livingston has the most positive, well, most positive together with Deception. Deception is a slightly more positive even than this. But at the Livingston case, but of course this is quite, I mean, there are some areas where you are losing. These areas are where the fastest ice streams are located, and are areas which are having a dynamic thinning quite strong during the recent decades. And in the case of Snow Island, is the one with the most negative value. In this case, you would think that is something similar to what we would find in other regions. And this is partly also because of some loss of frontal area, which is what we have when we have the reds, is mostly because some the sea terminating front, the Calvin front has retreated. And then in the case of Livingston, as Deception, as I mentioned, is also positive. This is a volcanic island, and the island comes like here. Here are only the different basins where we have the glaciers. And in the case of this is Low Island, is again quite close to 0. I lost the value for the whole thing. And then other cryospheric and environmental impacts of the recent cooling. I will try to go. I didn't check the time. and I have seen that it's really late, so sorry. Other observed impacts on the cryosphere. Then in recent years, these lower temperatures have had as a consequence a longer duration of the snow cover in different areas of the southern islands. Here is a reference for this. But this change in the snow cover has had an impact in the soil thermal regime, and especially in the permafrost, which is what covers the next slide. And here, basically, just to say it quickly, what we have to say is that during the recent years, both in the South Shetland Islands and this reference here, and in James Ross Island, so in Northeastern Antarctic Peninsula, there has been a decrease of the thickness of the active layer of permafrost. And that decrease has been up to at certain locations, for instance, in Livingston Island, at certain locations, the active layer, which is the layer that gets melted during summertime and then gets refrozen, in wintertime has become zero, the thickness. So has totally disappeared, the active layer. And also is nice to remark, or because it's something different from our usual work, the fact that there have been also observed impacts on the biosphere, especially respect with lichen growth rates observed in Livingston Island. Here we have an area where these lichens that you can see here, and you cannot see here, this is 2002, this is 2015. These are certain species of lichens which had died or have been killed by the fact of having, these were in this frontal moraine, in this area here, that was like this for really many decades, and recent conditions was something like this. They have been totally fully snow covered. That means that they cannot make photosynthesis. That then means that some of the species that are less adapted to the lack of sunlight just die. There is this publication of which we are also co-authors in scientific reports regarding to this. And then here you have the growth rates for in the 90s, just for the 2000s, and then for the 2015s, which you see the decrease in the last period, but also going below zero. Below zero means that these are decreased rates, and decreased rates can involve the disappearance of some of the species. Here, and of course, it depends on the species, different species of lichens. Some of them are particularly sensitive to this, and in particular, the ones that you see here are the ones that are most sensitive. But you see that from between this and this, they had some growth of all of the different elements, and here they were just virtually dead. And important also to mention that this fact, in fact, is known as snow kill, and this is expected to lead not only to the death of some lichens, but also has a consequence, an impact on biodiversity, because different species are have different sensitivities, and if we have that kind of events quite continually, some of the species, in particular these ones that I mentioned here, will probably disappear, and then with a decrease on biodiversity. So just some quick conclusions. So as we have seen, although we had a relatively brief cooling period, and the magnitude of the cooling was, especially in summertime, was limited, it has been sufficient for having an important impact on the regional cryosphere and biosphere. This would be not unexpected at all for surface mass balance, because we have seen that these glaciers are quite sensitive, highly sensitive to temperature changes, and also we know that the surface mass balance changes are just the instantaneous response of glaciers to atmospheric forcing. However, for other elements of the cryosphere with a slower response time, such as for instance permafrost, they have also noted this impact, and also we have seen that some elements of the biosphere have also experienced an important impact, which moreover can have an impact on the biodiversity. And this is just a final comment to say, final remark, that the cooling period seems to have come to an end, And this is the extended mass balance series covering up to 2019. And you can see here, in the case of Hurd, it's always more negative. We were showing only anti here. This is not included in the series for one particular reason, is that because of logistic problems during these campaigns, we had a later start of the Spanish Antarctic campaign. And then that has had an impact that we are still trying to solve to get more precise numbers for this. But anyway, it is clear that we have negative mass balance. We have come back to negative values during recent years, which has been in parallel with an increase in temperatures as observed in all of the stations in the South Shetland Islands. And in the case of Johnsons is always more positive, and you see that these negatives have been nearly zero, but they were previously all positive. We had this positive, and what we have here is not estimated yet. The estimate will be ready probably in a couple of months. This is going to be really quite negative because we had a really huge melt in the last season. So this is the acknowledgement, and then I will finish with this, which is just the announcement of the next lecture by Adrian Lackman, and I hope that he will be shorter than me. Sorry for having been so long, because I didn't check my clock. I did it wrong, and I should have been keeping. So that's it. Thank you.
Thank you very much indeed, Paco. Just to remind people what we usually do with questions, if you type your question or just that you would like to ask a question into the chat or onto Facebook, then we will ask you to unmute yourself and ask your question. It's certainly fascinating to see the climate change hotspots that used to be claimed on the Antarctic Peninsula is more variable than we have previously thought. So that was really, really interesting to see. Does anyone have a question for Francisco?
I think that the snow cover has killed 2 lichens, but I have killed the audience with such long talk.
Well, you have Ben Ditter saying thank you very much and greetings from Chile. Yeah, so it looks to me as though we may not have questions, but everyone is wishing, saying thank you and wishing you a happy new year. So. And I guess we should just say thank you very much to the audience as well, and hope to see people at Adrian's seminar next week. So yes, yeah.
I see that Hester is asking how reliable it is.
I don't see that. You'll have to answer that yourself. I don't see that question. Go for it, Hester.
Yeah, it is in the, I see in the chat that is how, well, you can ask by talking if you want, Hester.
Yeah, sorry. I'm just wondering how reliable is lichenometry in that region where you don't have a lot of independent dates. There's been a number of recent papers since 2015, how reliable lichenometry is in general. So I'd like to know if you have an opinion about that.
Well, really, I'm not an expert on this because, I mean, I was collaborating. I was a co-author of this paper because we were supplying and analyzing the corresponding ice cover, snow cover changes and the surface mass balance changes and how high was the equilibrium line altitude and so on in relation to the growth and decay of these species. But I could say that this Leopoldo Sancho is a SCAR member, and they have been studying, so he has been doing lichenometry all around the Transantarctic mountains, all across the, let's say, from the Ross Sea to the Antarctic Peninsula. And so he's a good specialist, and he has sometimes some doubts about but I mean, he's quite, he has, I would say that he's confident in the values that he's getting about the growth rates, even knowing that this is a really nebulous subject that is not that clear. But this person in particular is a specialist, and he's has a quite confidence in his results. But I mean, he's quite critical and in general, and in this particular case, he's saying that is what he has seen in this particular region, because for a long time he was motivated by the fact that there was a huge increase in the sizes of the different species and the diameters and so on. But then they were really surprised when they experienced and saw such a decrease for certain species. And they were quite sure. Even the bars were, let's say, admissible in within this environment.
Thank you. There's another question on lichenometry from Roger Clark.
Let me see, Roger Clark. Cool and recovery of the lichen in the areas that are being UN.
No, that's uncovered.
Okay. I said United Nations.
United Nations. they don't have that much power.
The way that are uncovered, recovery of the lichen. Well, as I said, I am not expert in this, but I know that lichens are really so. When they talk about death, I know that the lichens are some species that they recover. I mean, they go back to life even when you thought that they were totally dead. And it is true. I have heard recently also to Leopoldo García Sancho talking about this equivalent recovery when the snow cover has been coming back to previous values.
And
Okay,
Andre, sorry, Andre, you have a question about the ice velocities.
Yeah, I see the trend in the ice velocities. This is not really. I would say not really, because this is tricky anyway, because we are measuring the velocities in the net of stakes, for instance. But these are summer averages, winter averages, and year averages. And the main point here is that as the stakes get closer to the Kelvin front, then the velocities increase. And then the changes are so small that no, I mean, there are big changes because of getting closer. In the case of Johnsons, which is tidewater, there are huge increases as you change the position of the stake. So they are going faster and faster, but just because they are getting closer to the. But then if you do the averages and you try to recover to like to the original positions and so on, then the decreases are really negligible, yeah, mostly. And in the case of Hurd Glacier, it has so really slow velocities. The maximum are around 5 meters per year, and then our maximum in the center because there is melted base, and the end parts are frozen to bed because they have a small thickness, and then they are frozen to bed, and then they are slower in these areas. But the changes, again, in this particular case, are nearly nothing. I mean, are below the observational errors.
Thank you very much. Are there any last questions? I think we may have run out there, but thank you very much for a fantastic talk. Great way to start off the new year's seminars. And yeah, hope to see everyone next week. So thank you very much. And
thanks to all.
Good night, good morning, and all of those things to everyone.